Good morning, everyone. My name is Étienne Houzé, and I'm pleased to be here at the Access Conference to tell you about our works about a generic and modular reference architecture for self-explainable smart homes. So first, let's get a bit of context for explainable artificial intelligence. XAI means explainable artificial intelligence, and it can be roughly defined as a study of methods that can make machine-made decisions understandable for a human user. This topic has been quite trending in recent newspapers, but also it has been an active research field, as we can see a sharp increase in the number of publications regarding explanation and artificial intelligence. So if we wonder if we can bring this topic to smart homes, we may see that we have different benefits from it. Imagine that your Alexa at home is able to tell you the reasons for the room being too cold. So this can increase your trust towards the intelligent systems if it allows you to better understand the limits of the system. Alternatively, it can increase the performance of the system because you can make better, more informed decisions. So you can, for instance, decide to save a few euros by changing settings. Or it can facilitate maintenance because being able to tell you that it's cold because some components is unresponsive can help you making an early diagnostic, which can link to a better maintenance. So for all of these different reasons, explanations would be nice to have in smart homes. However, looking at the current state of the art of explainable AI, we see that there is not that many works that tackle this issue. And we mainly identify three main challenges that remain to explain smart homes. The first of these challenges is smart device heterogeneity. As you may know, smart homes are collections of different devices acting in the same house. So they are heterogeneous systems. You can have different devices, you have lamps, you have speakers, different presence sensors, thermometers, heaters, and all kinds of different systems. So we have different logics, different variables, different interfaces in the system, and we'd like the explainable system to be able to be generic enough to handle all of this heterogeneity of devices. Then we have the issue that some knowledge may be unavailable. What I mean is that, for instance, the heater doesn't really know the state of the window because this information may not be shared by the window to other devices in the house. So we'd like an XAI system that is able to preserve this kind of component privacy or non-disclosure of private or sensitive information. A second challenge that arises is that smart homes can have runtime changes. So they are what we call autonomic systems, meaning that they are able to self-manage to attain high-level goals. So examples of these features are, for instance, I can change the temperature target of the system, and the system will automatically self-manage itself to reach this new target. Or I can add a new component, a new heater into my system, and the system will be able to integrate it and to basically configure it without me having to intervene. Or I can have a thermometer that is faulty and that reports bad measures, and the system will be able to detect this behavior and to deal with it. So we'd like the XAI system to be able to present this kind of self-autonomic behavior and be able to self-observe, self-configure, and integrate all of this into the reasoning. In some sense, we'd like the XAI system to be self-aware. And finally, there is the topic of context changes. The context for the explanation is really important. And the context may change. In some sense, we can understand that the meaning of words can change. The notion of cold is not the same between summer or winter. So we'd like to have the XAI system that integrates these changes, so it is able to detect it and to integrate this change into the explanation reasoning. In order to deal with these three main challenges, we already designed a generic method, a high-level reasoning method that is named DCAS. DCAS stands for Decentralized Conflict Abduction Simulation. Basically, it breaks down the explanatory system, the explanatory reasoning, into 3 steps. The first of them is conflict detection. It's identifying a conflict and matching it with some formal representation. So if I say that the room is too cold, I match it with the conflict written down as cold room, so we have a Boolean proposition that is true, and then a score, which indicates the strength of the conflict, the strength of the inconvenience, for instance. So here, -30 indicates that I don't want the room to be cold, so that's why it's negative. Then I have the second step, that is abduction. Abduction is the inference from the observation to a possible cause. For instance, I observe that the room is cold, then I might infer that maybe the window is open, and because of this, the room is cold. Finally, I have the other step, that is simulation. Simulation is going in the other direction. I observe that the window is open. What would happen if the window instead was closed? So with these 3 steps, DCAS is able to generate an explanatory reasoning within the system. Each of these steps can be performed locally, and we just need an ignorant central coordinator to monitor the overall reasoning. By ignorance, I mean that the coordinator is only used as a naming and directory service. It doesn't have to know the state, the different observations of each component in the system. To illustrate this, let's consider this example. I ask why is it cold, so my request goes to the coordinator as this formalism with a proposition and the score. This request then is transferred to the component that has been identified as the most capable, which in this case is the thermometer. So the thermometer has to handle this request using its local knowledge and may propose that it's cold maybe because some window is open somewhere. Note here that the thermometer doesn't know if the window is open. It doesn't even know if there is a window. It just proposes this as a possible cause without knowing if it's the case. To know if it's the case, if the window is open, the coordinator will ask the window why it's open. So if it's open, and if so, why is it open? And to this request, the window will find that there is a possible action. Maybe we can try closing the window and see what would happen. So which, in our case, if this ends the conflict, I can have the following explanation. It's cold because the window was open. Now that we have designed the generic reasoning process, we need an architecture to implement this. And for this architecture, we start with the existing system that is composed, as I've said, of different devices. These devices, in yellow, are managed by different autonomic managers, which are in green in this picture. And we see that each of them present a specific interface that can be used to observe each component. So to this specific interface, we add what we call LEC, or local explanatory components, which are tasked to observe each individual component and reason on their local knowledge. Each LEC presents a generic interface that can be used to plug in the central coordinator that we call Spotlight. We call it Spotlight because, as I've said, it's only a naming and directory service, so it just puts into the Spotlight the LEC that is responsible for the current conflict. Note that the Spotlight is observable itself, so I can add a local component to observe it and reason on its knowledge, mostly to reason on the configuration of the system and the possible addition or removal of devices. Finally, I can add a user interface to interact with the user. So there is one issue remaining with this construct. It's that at the device level, we have variables, while at the reasoning level, we have propositions. And there is a difference in nature between the two of them. Because on the one hand, propositions, their meaning can change through time. As I've said, something cold, a room cold, won't be the same for summer or for winter. On the other hand, once some data has been recorded, we can no longer revise it. And furthermore, data we may not want to share it with any component in the system. So to do this translation operation, we add two new objects. The first one is the event, and the second one, the predicate. An event is defined only as a triple with a label, a timestamp, and a set of characters. It is a high-level representation of observations. So I can define called observations with the label, the timestamp of the occurrence, and a set of characteristics, for instance, the minimum recorded temperature and the device. On the other hand, a predicate is a Boolean function that operates over these events. So the predicate will associate a Boolean proposition to some events and possible arguments. So I can define a predicate for the location of the event, a predicate for its temperature, and maybe so my event is recorded outdoor, so it will be true to say that it's outdoor, but it's a cold event, so it will be false to say that that's a hot event. And on the one hand, events are immutable, so once something has been recorded, I can no longer revise it. On the other hand, a predicate meaning can be modified to adapt to the user's definition of words. Integrating this into the LEC, we see that we have two memories, a memory of events and a memory of predicates, that are filled with observations from the observed components, and then we detect events from these observations, we detect possible predicates that can be used. And then when there is a request from the spotlight to explain something, so this request will be a proposition and a score. So the first step would be to match, to see if there is a possible match between the request and the known events and predicates. If there is a match, then all of the information, the proposition, the predicate, and the event will be fed into the abduction unit, so I can find if there is a possible hypothesis for the issue. If there is one, so for instance it's called because the window is open, then this will be the final answer from the LEC back to the spotlight. Note that we only exchange propositions in the process. Both variables and events, which may not be disclosed, are confined within the LEC, and as such there is local knowledge that is not shared with anyone else. So to see if our architecture can be implemented in practice, we developed a proof of concept demonstrator that is based on a model house. So the realization looks like this. So we have a central unit which hosts the spotlight and different utilities, and we have different Raspberry Pis which simulate the different embedded components and host the different local explainable components. The result looks like this. So we have a model house with different devices, and these devices are connected to Raspberry Pis that are located beneath the floor of the model house. If we can play some situations with this setup, and the output will be in the form of explanation trees. So on the left-hand side, we have the base request, so why is the room cold? And this request will then be transmitted to the temperature controller, which is the blue node. And this controller will say that, yes, there is a possible abduction. Maybe it's because a window is open that the room is cold. Then the request is transmitted to the window, which doesn't know how to simulate things. So the window has no other option than giving up. But if we add a simulation module to the window so that now it is able to think and to imagine what would happen if we close it, then I may have this following tree. So the beginning is the same, but now the window is able to find the green node, that is the action. Maybe it's possible to close the window and see what would happen. If I do so, then I simulate that this would end the conflict of the room being too cold, but this can rise another conflict. Now the CO2 concentration is too high, and I may have the following explanation. The room is cold because the window was open, and the window was open to ventilate the room. Another example that is interesting is that if I ask why it's cold, and that the system has to change its meaning of cold to match my request, so then the system is able to observe that it had to make this change in a predicate, and this change can be used as a possible cause. So in this explanation, the system is able to tell me that the room is cold because it had to change its meaning of cold to match my input. So in other words, it was cold because the system definition didn't match mine. And with this kind of example, we may reach our final conclusion. So in these works, we present a high-level modular and generic architecture for explainable smart homes. This architecture tries to answer the following challenges: runtime device changes, runtime context changes, and the heterogeneity of smart devices. We use a proof of concept model house demonstrator to validate our approach and generate some interesting examples. And finally, our approach aims at being modular and generic, so it is meant to be enriched with more advanced techniques for conflict detection, for simulation, and for abduction, which opens up the way towards future works in the area of explainable smart homes. So with this, I want to close my speech, and I would be glad to answer any questions if you have. Thank you very much for your attention.